AB Calculus Note Card 14, Differentiability. This is the 14th video lesson in the series that shows Stacy McMullen's development of the note card system with the Dallas Independent School District. Differentiability. A function is differentiable at x equals c. It's continuous at x equals c. So the first thing we need to have this thing work for differentiability is continuity. Okay, continuity. And for continuity, you can look back at note card 6. And so the limit as x approaches c from the left side equals the limit from the right side. So this will be left limit equals right-hand limit, RH for right-hand limit. And we'll see tests for that. It is possible a function to be continuous at x equals c and not differentiable at x equals c, a cusp or a corner or a vertical tangent. So a cusp is kind of a weird thing. What is a cusp? Well, cusp is something like this, where it's not exactly a corner, but it's sort of like the way to say it would be like a jagged edge. Okay, so function would not be continuous, differentiable there, continuous but not differentiable. Or you could have like this, a corner, or you could have a vertical tangent line, something like this. And in these three instances, you would not have differentiability at that cusp, at that corner, or at the point of vertical tangency. So things to look out for. Now we'll go to the problems. 1, the graph to the right, this graph here, has a vertical tangent line at 2, 0 and horizontal tangents at 1, -1 and 3, 1 for what values of x in the interval from -2 to 4 is f not differentiable. Well, here we have at x equals 0 because we do not have continuity. So at x equals 0 because not continuous, and I'll abbreviate continuous. Okay, and also says a vertical tangent line at 2, 0, right? That's a vertical tangent line, and also at x equals 2 because vertical tangent line. Okay, 2 is g differentiable at x equals 0, justify. Now it so happens that in the previous note card 13 on normal lines, problem 3, we worked out differentiability for a problem similar to this one. Well, first of all, we have to demonstrate continuity, and for continuity you need 3 conditions. You need to know, I'm going to test for continuity here. Okay, test continuity. You need to know, 1, that g of, in this case 0, exists. And does g of 0 exist? Yes, because of this thing right here, where x is greater than or equal to 0. So if we plug in 0, we say 1, because 2 times 0 plus 1 n is equal to 1. 2, the limit exists, and for that the limit as x approaches, in this case 0 from the left, of g of x has to equal the limit as x approaches 0 from the right side of g of x. Is that true? And so for that, we say, okay, we have quantity x plus 1 squared, and then that'd be the left one. On the right one, we have 2 times x plus 1. And now plugging in 0, we're going to have 1 squared, which is 1. And then we're going to have 2 squared, but 2 times 0 plus 1. And we're going to have 1. So 1 equals 1. And so 3, we have g of 0 equals limit as x approaches 0 of g of x, which equals 1. So therefore, continuous at x equals 0. Now we need to do our test for differentiability continues, because we're going to find the derivative here, and so we say that g limit as x approaches 0 from the left side, not of g of x, but of g prime of x, equals the limit as x approaches 0 from the right side of g prime of x. So for that we have, well, let's just take the derivative of this thing here, which is going to be, our derivative is going to be 2 times x plus 1 to the power of 1 times the derivative of the inside, which is 1. So that'll be the derivative of the left side. On the right side, our derivative will be 2. And if we plug in 0, we're going to get 2 times 1 equals 2. So check. So limit as x approaches 0 of g of x exists. So since we have continuity and the limit of g prime of x exists as x approaches 0, therefore we have g of x is differentiable at x equals 0. And again, problem 3 in that last note card 13 is a similar type problem, as it turns out. 3, let f be a function such that limit is as h approaches 0 of f of 2 plus h minus f of 2 over h equals 5, which of the following must be true. And so what this tells you is that we have this tells you essentially, if this function is f, it tells you f prime of 2 is equal to 5. That is what this is saying, okay? And to have an f prime of 2, you need to have first continuity by definition, okay? And you need to have differentiability by definition, because there's no way this could exist if you didn't have a differentiable function. And is the derivative of f continuous at x equals 2? Well, we really don't have any way of knowing condition 3. So the only things that we can conclusively exclaim is that Roman numerals 1 and 2 are correct. Okay, again, double asterisks, actual free response AP calculus test problem. For what values of k and p will f be continuous and differentiable at x equals 1? So again, we're going to set up our test for continuity. And to do that, we say limit as x approaches 1 is our breakpoint. From the left side of f of x is equal to the limit as x approaches 1 from the right side of f of x. And the left side limit, and we see that we have an equal, we have less than or equal to, so we know that f of 1 is defined. So left-hand limit is going to be 2x, left-hand side is going to be 2x minus x squared equals the right side, which is going to be x squared plus kx plus p. And so now we're going to just substitute in 1. So we have 2 times 1 minus 1 squared equals x squared, which is 1 squared, plus k times 1 plus p. Now simplifying out, on the left side we have 2 minus 1 equals 1 plus k plus p. And now we have on the left side 1 equals 1 plus k plus p. And if we subtract 1 from both sides, we have 0 is equal to k plus p. Now we don't know what k and p are because we have one equation and 2 unknowns. So now we're going to come up here and do the test, the final test for differentiability. And then to do that, we have the limit as x approaches 1 from the left side, not of f of x, but f prime of x, equals the limit as x approaches 1 from the right side of f prime of x. And so what we have, the left side, f prime, is going to be 2 minus the derivative of x squared, which is 2x. And on the right side, we have 2x, and then the derivative of kx is going to be simply k, and the derivative of p is 0. So now we're going to just substitute in x, 1 for x, so 2 minus 2 times 1 equals 2 times 1 plus k. And so on the left side we have 0, on the right side we have 2 plus k, and so subtracting 2, k is equal to negative 2. So that's one of our answers. And now coming back to the first equation, we have 0 equals negative 2 for k plus p. I said negative k, 2k, not right, negative 2. K is negative 2. We have 2 plus p. And adding 2, p is equal to 2. So p is equal to 2, k is equal to negative 2. And you can just plug these in to check to be sure. So if we have 2 times 1 minus x squared, the left-hand side, we have 1. On the right side, we have 1 plus negative, let's see, kx will be negative 2 plus 2. That checks out. And then, so these will check out. I hope this has been helpful to you. Good luck, and thanks for viewing.